Here are the answers to the summative assessment on chemical quantities. You would have had either one of these two questions, but not both. The first one gives you an image that shows 1 mole of several elements. Which sample has the greatest mass? So if we know they're all 1 mole, then we can just look on the periodic table and see which has the greatest molar mass. And from there, it should be the lead. So it's not necessarily which one seems to be taking up the most space, like the aluminum sample seems really large, or the sulfur and tin beakers are really full. It depends on the size of the atom. And so if we look on the periodic table, we can get the molar mass, the mass of a mole. The second one gave you some element samples, and there were masses attached to each sample. These just happen to be the molar masses. If you look up sulfur, magnesium, tin, silicon, and copper on the periodic table, you will find that these masses are what's listed. They are the molar masses, which means they're the mass of a mole, and 1 mole of anything is the same number of particles, 6.02 times 10 to the 23rd atoms in all of those samples. Similar here, you would have only had one of these two. Which sample will contain the most particles? And so you've got 10 grams of everything. And so we kind of used the example earlier of like a rock and a feather, that I could have 10 grams of rocks and 10 grams of feathers, but because feathers are each really light, to get up to 10 grams, you're going to need a lot of feathers. Maybe it's only like 1 or 2 rocks that already give you a mass of 10 grams because individual rocks are just heavier. And so kind of similar here in the first example, if I look on the periodic table, lithium has the smallest molar mass, and in the second example, it's helium that would have the smallest molar mass. So the atoms are the smallest, they're the lightest, so it's going to take the most helium or the most lithium atoms to get me up to that 10 gram sample. With this question, you would have had one of these 3, but not all of them. These are great. They give you different amounts of carbon dioxide, and in each, I want to rank them from greatest number of particles to least number of particles. The problem with all 3 is that you've got these quantities that are in different units. And before I can really compare the amount of particles in each sample, I in some way need to convert them all to the same unit. Now, it wouldn't matter if you put them in moles or molecules, but in some way you had to get them all to the same unit. So I just put them all in moles. And so I took like the 42.5 grams of carbon dioxide and I got it into moles. Well, in the first sample question, then I had 0.654 moles in choice 2, and then I took that 3.9 times 10 to the 23rd molecules and switched that to moles. And it makes sense because 3 times 10 to the 23rd, that should be about half a mole. So I had a little bit less than half, 0.482. And from there, it was easy to rank them. Once I had them all in the same unit, then I could go largest to smallest. Now the key was that you probably either wanted to switch them all to moles or all to particles like molecules, but then you would have been dealing a lot with that 6.02 times 10 to the 23rd, and I don't know, it's just clunky. So I went with moles. So in the red example, I took my 4.8 times 10 to the 23rd molecules, canceled molecules, switched her to moles. The second choice was already in moles, and then I took my 18.6 grams and converted that to moles. I wanted to cancel grams, so the 44.01, that's off the periodic table. That's just the molar mass. That's 1 carbon plus 2 oxygen. And so yeah, now I can easily rank these by greatest moles to least moles. Moles is a unit that represents a quantity of particles. And then same thing with the last choice. The first number was in moles, 0.851. And then I ended up with about 0.693 moles when I converted 30.5 grams into moles. And then the last one was like a little bit more than half, which again makes sense because 3 times 10 to the 23rd should be about half a mole, and I've got a little more than half. So these guys then all rank from greatest particles to least particles. Getting them in the same unit was the key. And I think moles is maybe the easiest. Similar with this question, you would have just had one of these two versions, but now you got another one if you just need another sample question to study. Categorize the following quantities as greater than, less than, or equal to 1 mole. Okay, so all I did was start by looking on the periodic table to get the molar mass of all the particles. The molar mass of water is about 18 grams. I just added them right on my calculator. 2 times hydrogen plus 1 oxygen. Now the key to the other ones is that we needed to write the correct formula. So calcium is +2, oxygen is -2. So that's neutral. I just added 1 calcium and 1 oxygen and got about 56 grams per mole off the periodic table. And then zinc, 2 nitrate. Zinc is +2. And then I had to look up nitrate on my polyatomic chart. NO3 -1. So again, the key was getting those formulas right. Maybe the most important skill from first semester is being able to write good ionic and covalent formulas. So I had zinc +2 times the nitrogen and 6 times the oxygen. I got a mass of about 189 grams. Okay, so then I got the molar mass for all the compounds. Any element I can just look up on my periodic table. So when I see that the molar mass of water is 18 grams, well, yeah, 35 grams, that's more than a mole. It's almost 2 moles. When I look up aluminum on my periodic table, the molar mass is about 27 grams. Anything more than that is more than a mole. The 56, that's exactly what I calculated. So 56.08 grams of calcium oxide, that would be a mole. And on my periodic table, 12.01, that is the exact molar mass of carbon. So those would equal 1 mole. But when I look up chlorine, I see the molar mass is about 35. So anything less than 35 grams is less than a mole. And the zinc nitrate, the molar mass is about 189 grams. So anything less than that would be less than a mole. And then I did the same thing with the second example. So if you had the second example in red, I just did kind of a little sidebar and did the calculation for the molar mass of all the compounds. So magnesium oxide was about 40 grams per mole. Water was about 18. And then again, you had to just make sure that you wrote some of these formulas correctly. Copper 2 hydroxide is CuOH2. I added my masses with that copper hydroxide. I made sure to distribute so that there were 2 oxygen and 2 hydrogen. So the periodic table gives me the mass of 1 mole. So yeah, 18 grams of water, that's the molar mass, that's 1 mole. When I look up helium, yeah, the periodic table says 4 grams per mole. That is 1 mole then if I have 4 grams. But the magnesium oxide, if I have about 48, 49 grams, that's more than a mole. 1 mole was only 40 grams. Sulfur's molar mass is only about 32 on my periodic table. So anything more than 32, that's more than a mole. Iron's molar mass is about 55, 56 grams per mole. So anything less than that is less than a mole. And then that 80.21 grams of copper hydroxide, that is less than a mole. A mole would have been about 97 grams. I like that one. It's really just about using molar mass and using your periodic table. Here you would have had one of these too, so you got another one to study. Element X forms a compound of sulfate. Having the formula X3, PO4, 2. Alrighty, so from there, I have the molar mass of element X, and I can just find the mass of all the other elements, the phosphorus and the oxygen, making sure that I distribute it properly. So if I have this X3, PO4, 2, there's 3 times element X, there's 2 phosphorus, and there's 8 oxygen. Then I just added it all up. And same thing with the second example. Now I've got X sulfate. The formula is just a little different. X2SO4, 3. So there's 2 times the mass of element X, 3 times the sulfur, and 12 times the oxygen. Add them all up, and I got the molar mass. Here you had element Q that forms 2 different compounds with oxygen. They gave you in each case the molar mass of element Q and asked for the percent mass coming from element Q. So we're doing percent composition, which is just the total mass of an element divided by total mass of the compound. And so I found the total mass of element Q. In the blue example, there were 2 atoms of Q. They're each 10 grams. In the second example, there's 2 atoms of Q. They're each 8 grams. So I got the total mass of Q divided by the total mass of the compound. So I had 2Q, and then I added 5 times oxygen, or in the red example, 3 times oxygen, to get the total mass of the compound. Obviously, element Q is not a real element, but I can do this calculation as long as I'm given the molar mass. And then we just divide. We divide and multiply by 100. So in the first example, we're about 20% Q by mass. And in the second example, we're about 25% by mass. Awesome. The most common boo-boo is just sometimes on top, people don't put the total mass. So if there's 2 atoms of Q, you got to multiply the mass of Q times 2. Empirical formulas are the simplest ratio of elements in a compound. So if I have 2 compounds that have the same empirical formula, it means that I could simplify the ratio and they would both simplify to the same formula. So in the top example, C3H6 and C4H8 both have a 1:2 ratio of carbon to hydrogen. And in the second example, C2H2 and C6H6 both simplify to a 1:1 ratio. So that's the empirical formula, the simplest ratio. If I simplify or reduce the ratio, we're looking for compounds that would simplify to the same empirical formula. Here we're looking for an empirical formula, and we're given moles. Now, often we were practicing these and we had to calculate moles, which kind of adds an extra step. And here we were already given moles. We had moles of potassium, moles of chromium, and moles of oxygen. And so if they're already in moles, then I'm just right off the bat looking for the simplest whole number ratio, which obviously these aren't whole number ratios. So the first trick to try is dividing by the smallest. Often that'll fix it, and in both of these examples, it did. So the first one, I got 2 potassium, 1 chromium, and 4 oxygen. If you had the second version, real similar. Your moles of each element were already given, and to get a whole number ratio, first try dividing each by the smallest. And then we cross our fingers and we hope that gives us whole numbers. And it did. 2 potassium, 1 selenium, and 3 oxygen. Good stuff. All right, then we got to the last question where we were working these out, showing our work, showing all our steps, and then we sent in a picture of our work. And the key is to show your work, to show all the steps for full credit. Both of these were real similar. They just had different elements and different numbers. The first example was 5 grams of a chromium oxide compound heated in the lab. After intense heating, the oxygen is removed and that just goes off into the air, but then you're left with the metal. The solid metal is left behind. Now, if I subtract the amount of chromium from the original chromium oxide, I can get the mass of oxygen. I did the same thing in the other version. There was a 4-gram sample of vanadium oxide. After intense heating, 2.24 grams of vanadium metal were left behind. So I just took the 4-gram sample of vanadium oxide, subtracted the mass of the vanadium, and got the mass of the oxygen. So that in each case, if I add the metal plus the oxygen, it should add to the total mass of the sample. Then once we had grams of each element, we could turn them into moles. So in both cases, I had grams of metal, grams of oxygen. We turned them into moles. When I got to my moles, I just tried to leave a couple digits. It doesn't really matter, just maybe like at least 3 digits. Because in none of them did I get whole number moles. So I always then had to divide by the smallest, trying to get a nice whole number ratio. If you get a little too ambitious and you round a little aggressively, when you get to the point where you're dividing by the smallest to get a whole number ratio, it might not be a nice whole number. If you jump the gun a little bit and you round it too much. So that's why I like to usually leave at least 3 digits. Then I divided by the smallest, and in both cases, I got a 0.5, which is okay, because from there I can just go and multiply everything by 2. I'm trying to keep the integrity of the ratio, like 1 to 1.5, 1 to 2.5, but I just need to make it a whole number ratio. So by multiplying everybody by 2, then I got a ratio of 2 chromium and 3 oxygen, or 2 vanadium and 5 oxygen. So these are the steps that we were looking for. Once you had the mass of each element, we needed to switch them into moles and then divide by the smallest to get a whole number ratio. Often that fixes it. This is like worst case scenario, where I get a 0.5, but I can work with that. Just multiply everybody by 2. All right, then the last 2 questions kind of went together. So here's one version. If you had the version with bromine, this is for you. If your question had fluorine, feel free to fast forward. And again, you've got another example now if you want to study and practice for a retake. Okay, so in both questions, we have an unknown compound and they've given us the percent composition. If I assume a 100-gram sample, then I can use those percentages as masses. And once I have grams, I can switch them into moles. So same thing, once I switched all my grams into moles, I tried to leave at least 3 digits, sometimes 4. I just wanted to leave enough so that I felt confident when I got my whole number ratios, which these ended up becoming nice whole number ratios when I divided everybody by the smallest. The smallest was my 0.813 moles of bromine. And so here too, like if you would have just divided by 8, or I should say 0.8, you might not have gotten perfect whole numbers. But if you leave a little more, 0.81, 0.813, and the more precision you leave, the better your ratio will be. Now I got a nice 3-7-1 ratio. So there's my empirical formula. But then in question 3, they told me the true mass of the molecule was 246 grams per mole. So I just took my periodic table and kind of quickly added the mass of C3H7Br. And I got about 123 grams. Which then all I have to do is compare that to the true molar mass or molecular mass, 246. And then found that, oh yeah, the true molecule should be twice as large. So then all I have to do is double my ratio. Instead of 3-7-1, it becomes 6-14-2. And then we got it. So that's all the work that we were showing for both parts 2 and 3. Getting our percentages into masses, masses into moles, getting that whole number ratio. And then part 3 was comparing the mass of my little empirical formula to the true mass of the molecule. Now, if you had the version that used fluorine, then this is for you. We had percent composition of all elements in our compound, but by assuming a 100-gram sample, we can turn those percentages into grams. Then I can go grams to moles. The idea is that we're looking for the ratio of atoms. How many atoms of carbon to how many atoms of hydrogen to fluorine. And moles is a unit that represents a quantity. So if I can get those grams into moles, then eventually I can get a nice whole number ratio, which none of these came out to be whole numbers. So I divided them by the smallest and got beautiful whole numbers right away. But again, it does help to leave, I usually go like at least 3 digits. So if you would have maybe just rounded to like 1.6 instead of 1.61, then maybe you wouldn't have gotten a perfect whole number. I mean, it's probably still close, but leaving a little bit of extra precision might help. From there, after I got my little empirical formula, in part 3, we were looking for the true mass of the molecule to be 124 grams per mole. Well, when I found the mass of my little empirical formula, I only got about 62, which then tells me that the true formula should be twice as large. When you divide your true molecular mass by the little mass of the empirical formula, you should always get a whole number. That whole number multiplier means that instead of the ratio being 3:7:1, it should become 6:14:2. And if I wanted to double check to see if that's the right molecular formula, if I add C6H14F2, I should get a mass of 124 grams.